Okay, very good. All right, welcome back, everyone. So, hope you had a great week. Today's lecture will be about Introduction to Multimodal AI. So, logistics first. For the project, thank you everyone for submitting your proposals. It was all a pleasure to read. I've tried to give a good amount of feedback on the proposals. I've also assigned a primary TA, one of David and Chanakya, to your projects, and I CC them in an email. And the goal is to meet with myself and a primary TA alternating every week. So with me every other week, with a primary TA every other week. On average, every week you get someone to take a look at your progress. All right. And our goal is really, take these projects and really turn them into, state-of-the-art, really good research level work. Reading assignments. The second reading assignment is due tomorrow, Wednesday, in preparation for this Thursday's reading discussion. Again, 2 papers, mostly around the theme of modern AI architectures. One of the papers is about scaling laws of these modern autoregressive models. Scaling law essentially meaning how does performance scale as you put in more data and increase number of parameters in your model. And surprisingly, there's a pretty nice trend to these scaling laws. So you could essentially predict what the performance would be as you scale up your models. That's the first paper. Second paper, also a very interesting insight on perhaps you don't need all tokens to do autoregressive pre-training of your models. Some might be more important than others, and therefore there's implications on how you could perhaps more efficiently train your models. All right, so project, start meeting with us and make progress on the projects. And for reading assignment, that'll be due tomorrow and discussion on Thursday. Great. So what have we seen so far? We've kind of covered basic foundations of AI, looked at introduction to AI and AI research, different forms of data, their structure, information within them, ways to learn from data, and also we covered at a very high level a unifying paradigm of different model architectures, including sequential, convolutional, spatial, and models for sets and graphs. Now, naturally, a lot of problems in the real world are also going to involve many different data sources, many different modalities. This is an active area of research. So in the next 3 weeks, up until spring break, we'll be covering broadly a bird's eye view on different paradigms in multimodal AI. Today will be more introduction and aligning different modalities. Next week will be about how to better fuse the information between different modalities. And finally, week 7, we'll look at this idea of transfer. You might not have a lot of data in the modality that you care about, but you could use some other more common modality to supplement your information. All right. So that's just an overview of today's lecture, Introduction to Multimodal AI, some core principles and challenges, and diving deeper into this first challenge of alignment. So before I start, a little bit of behavioral history about multimodal AI. Like many things in AI, it really started from people who are looking at psychology and human behavior. And before this psychologist called David McNeil, before he did his line of research, most people thought that we primarily communicate using language, and anything else, such as our gestures and our voice, was just secondary, not very useful, and would not displace language. And David McNeil came up with this experiment. It's called the McGurk effect, which really shook some of the predominant thinking at that time. So I'll demonstrate this effect by playing 2 videos, and I want you to just quickly tell me what's the similarities and differences between these 2 videos. So here's the first one.
Ba, 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 ba.
Okay, first video, and here's the second one.
Ba, 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 ba.
Okay, who can tell me what is interesting, either in similarities or differences between these 2 video clips? Mike.
Similarity in visual information, but in sound, first one was ba, and the second one was fa, even though like very well masked. Like the
Similar in visual information, but different in sound.
Yeah.
Anybody else in counterpoint? Yes.
I'm not sure that the sounds are different. I think maybe just the visuals are different, and since the lips look differently, we think it's a different sound.
And Oscar, you had some thought as well?
So if I didn't have the visual information, I would like
Yes.
call it with the same sound.
Yes.
But seeing that visual information would be the limit.
Yes. So I thought you raised your hand. That's why I call it. But anyways, that is, that's, I think most of you got the key idea. Of course. When I give this talk to many people, half the people on the laptops, so they go, oh, have you even played the second clip yet? Because if you're only on a laptop and when you're listening to it, you realize that the audio clips are exactly the same. Right? And if you start looking at the person's lips, you can see that the first person is doing ba with a B, second person is doing fa with an F. So our perception of the same audio clip can actually be very different based on how the person is saying it. So that really kickstarted this first era of multimodal research back in 1980s, which is this behavioral era, realizing that people, when we recognize speech from others and interact with others, actually use a good mix of different communicative modalities. Because that was more behavioral era. And then naturally, there was an ambition to build AI tools, computational tools that could replicate this behavioral perception of different modalities in humans. After the single computational era using AI to just replicate, came this interaction era where multimodal HCI and multimodal interfaces became really popular. So you had AI and human interacting with different modalities. And finally, nowadays, we have this deep learning era. Ever since the 2010s, we've seen huge amounts of GPU, huge amounts of data, huge amount of large models that really revolutionized this space of multimodal AI. And of course, as a sub-era, there's this foundation model era that really started in the 2020s, where we really seen the limit of scaling, the huge potential of scaling these large transformer models for single modality and multimodal tasks. So just historically, what tasks did people care about? I gave the example of audio-visual speech recognition, where your goal is to recognize what the person was saying from both audio and visual. So that started from this behavioral era, and actually was the first kind of task that people applied computational methods to, audio-visual speech recognition. Soon after came a lot of this early boom in internet-based data, so there was lots of interest in building systems that could digitize multimedia data on the internet. So given content, can you retrieve videos? And soon after that, there was lots of interest in recognizing human affect and emotions from our multimodal behaviors. Once we started getting into the interaction era, there was systems based on recognizing events in videos. There's work in recognizing sentiment and emotion of multiple people interacting with each other. And something that really kickstarted some of this, multimodal deep learning work was on image captioning. So if I give you an image, can you come up with a right caption for the image? And that was kind of the birth of modern language and vision research. And of course, within the past couple of years, we've really seen a ton of applications in multimodal deep learning. Right, in multimodal deep learning, from captioning images to captioning videos to writing descriptions of videos and then people found that captioning was really cool, but it was really hard to evaluate, right? How do you evaluate whether a given caption for image or video is correct? It's so subjective. So then people converted captioning into question answering. So if I give you a question about a particular video, how do you train an AI system to give me the right answer? So that was visual question answering. And again, people extended that to video-based question answering. And then it went from static systems to just writing one caption and answering one question. AI systems capable of holding multimodal dialogue. So given a particular image, referencing and conversing in a dialogue with humans about those modalities. More large-scale YouTube data became a source of data to pre-train all of these video models that could recognize and caption and retrieve different types of videos. Soon after, we saw lots of work in autonomous agents. So this was agents that are able to navigate using vision and language. So you might give it some instruction, like go there and then turn left at the nearest gas station. So those are agents capable of navigating based on vision and language. And of course, self-driving cars also do a lot of multimodal fusion of different visual, language, and sensory information. And nowadays in generative AI, we've seen a lot of applications that are taking in text to generate images and videos, right? These generative text to image video generative models. And finally, probably the biggest application today is these interactive agents on your computer, and your robots that can take in lots of data and are grounded in either the digital or physical world to complete difficult tasks, and many more. So that's just a brief history of various tasks that multimodal AI has made an impact on. So in the first part of today's lecture, we're going to just cover an introduction to multimodal AI, and then in the second half, we'll dive deep into some of these core methods. And a lot of this will be based on the survey paper that we have on foundations and trends in multimodal AI. And if you're interested in longer versions, we give tutorials at international conferences. So firstly, what is a modality? A modality is some data source representing a way in which information is expressed or perceived in the world. So like all forms of data that we've seen in AI, you think about some sensor, which is collecting your data, such as cameras or microphones. And you think of it as a spectrum from more raw modalities closer to a sensor to more abstract modalities that are further away from a sensor by doing more processing. So you can think of a raw speech signal from a microphone or a raw image taken from a camera as raw modalities. You can start extracting language from your speech signal. You can detect objects from images. You can extract sentiment from language, and you can categorize the object. So all this becomes more abstract information that you could even represent as words, right? Positive sentiment, or this is a table, or this is a chair. And as we've seen, the raw data can be very different. All the data comes from different types of structure and different dimensions. But as you start processing these different data modalities using AI systems, like these model architectures that we've seen, you're basically learning abstractions. You're learning abstractions and semantic information from different forms of data. So there's a possibility of bringing them closer together with each other. So multimodal problems are therefore those with different modalities. And when different modalities, multiple modalities are in the picture, there's often several challenges. These are challenges of firstly heterogeneity, the fact that different modalities are very different, and processing them together will cause difficulties. And the idea that there are some interconnections between your modalities. And we break down this word interconnections into first connections, so just two modalities themselves having some connected and overlapping information, and this idea of interactions, that there is some fusion that goes on to create new information when they're brought together for some task. So in more detail, this idea of heterogeneity should again be seen as a spectrum representing more homogeneous modalities with more similar qualities and representations to more heterogeneous modalities with more diverse qualities and representations. So you can think of images from two cameras as being more homogeneous. They're both visual modalities. They both have this spatial structure. They're both sensitive to the same type of noise from your camera blurs. So they're more homogeneous, but again, they're giving you different information, right? Different angles, different viewpoints of the same object. And then you can think of something that's more different, for example, text from two different languages, English, French, English, Chinese, different language families would have different structures and different grammars and different vocabularies. But they're still kind of similar because you can train a model to translate between one language to another with sometimes perfect information and sometimes losing a little bit of information. Then you can think of language and vision, images and text, they're much more different. You start to see their differences. And you can even go to something like language and sensors, which is even more different because at least in vision and language, you can think about a language to describe the image, but is there even a language that can successfully describe sensor data? So these are more different modalities. Yeah.
What do you mean by qualities here?
So everything in the modality profile that we've seen, so the base elements themselves, the distribution of elements, whether the data is discrete or continuous, what kind of information they contain. And I just highlighted structure and representations because those are kind of perhaps slightly more important qualities to consider.
It's not about the image quality or the language quality. It's just about the modality.
Yes, the Yes, not actual quality, but just the profile, the information, the properties of the modalities. Okay. And abstract modalities are more likely to be homogeneous. We've seen raw modalities are those that are collected closer to the sensor, so raw image and raw sensor data. Abstract modalities are the ones that undergo more processing, so extracting whether I'm happy or sad from my speech signal and whether I'm happy or sad from maybe my physiological sensor. So abstraction allows you to essentially bring heterogeneous modalities closer to each other. All right. So that's the first principle, that modalities are heterogeneous and therefore different. The second key principle in multimodal learning is the fact that when we just look at these modalities, there's often going to be some shared information that connects them together. And again, you want to think of this as a spectrum, with shared and unique information, and cases where there's more overlap, less overlap, and maybe settings where modalities are completely independent from each other with no overlap. So given any pair that, for example, co-occurs in the world, for example, image and text, you can see that there are some connections. They're both describing teacup and sofa. But for example, there's a lot of information in the image that is not captured in the caption. For example, the color of the sofa, the size of the table, even the presence of the table, all these are not really captured in language. So modalities in general have some connections, but not perfectly overlapping in information. And finally, interactions. So interactions describes this phenomena where when you bring your modalities together and you try to combine them, some new information will typically emerge for your task. And so for all these modalities and your task, one type of common interaction that people care about is this idea of redundancy, where both modalities give you some common information, and your goal is to really exploit this common information. So if I'm saying something positive, like this movie is great, and I'm smiling at the same time, then this is the idea of redundancy. You're reinforcing the idea that the person really liked the movie. That's in opposition to uniqueness, where there's only information in one, not in the other. For example, you're saying something slightly positive, like the movie does a good job developing the characters with neutral facial expression, and one of these has the unique information. So the challenge here is to identify which one has the right information and which others you should maybe throw away. And finally, synergy. So this is the idea that this information only emerges when you fuse the modalities together. They might be saying something, wow, it seems positive, but with some anger or frustration on your face. And then you can infer that this person might actually be sarcastic about this topic. So you have to look at both. You have to compute that there's some differences between the modalities, and that indicates sarcasm. So that's a key idea of interactions. So at a very high level, multimodal problems are those that involve heterogeneous, connected, and interacting data. Heterogeneous because data sources are different from each other, and there's difficulty in processing different sources. Connections because these modalities overlap in some information, and interacting because different parts of the information are going to combine when you try to fuse them together for some task. All right. So that's a brief explanation of what multimodal problems are. So then we'll cover why is it hard? What are some unique challenges in multimodal AI that are typically not seen in single modality problems like computer vision and NLP separately? And what are some of the state-of-the-art methods to deal with these challenges? So all of these multimodal models look something like this. So multiple modalities using different colors and shapes to represent them. And I'm also breaking down these modalities with elements, right? These might be words in the sentence that you're saying. It might be image regions in some big image that you're trying to process. It might be time steps in long-range sensor data that you're looking at. So just like how, in all of our discussion about machine learning, it's all about breaking things down into individual parts, learning representations, and then aggregating information, we're going to use a similar schematic over here. And typically, you're designing some AI system that brings it together as input multiple of these modalities, and either learns a representation or predicts a label as the output. right? So essentially, we're looking at what really goes in here and what are the challenges in designing the components within this block. So at a high level, there's going to be 6 challenges that makes multimodal AI difficult and unique and interesting to study. The first challenge is this idea of representation, right? So you have data that's different modalities, there's some heterogeneity between them. How do you learn the representations that can essentially bring them together and combine them in the right way? So representation is often a core building block in almost all problems, right? When you start with data that's raw, it's just collected. The first thing you always got to think about is how to represent your modalities. So for simplicity, again, this is the schematic. You might have data coming in with different elements, for example, multiple words that you're saying, multiple time steps in sensor data. We're just going to look at it more simply as just one element in each. We're just going to care about representing one element in each and ignoring the rest. We'll look at the rest in the subsequent challenges. Okay? So there's 3 key ways of doing representation, each achieving different purposes. One way of doing representation is what we call fusion, right? So you take in 2 elements, you might have already some representations for them separately, but how do you bring them together into one common representation that best uses the information in some appropriate way? This fusion might exploit the overlap in the information. It might be one that picks the right modality depending on the information. Maybe it might combine them in more sophisticated ways to capture some synergy between them. So in general, one class of methods is called fusion. Our second class of methods are what we call coordination. These methods take in your 2 elements and learn representations separately for them. Right? You have one, the first one for the second one. But it's not independent because they're going to align these 2 representations using some similarity function. So enforcing that there is some structure between these 2 representations that you learn. There's a lot of research that goes into how, for example, you can define this alignment between them. This is more useful when you might want to do retrieval, for example. You define this function as cosine or dot product similarity, then you can take something, learn a representation, find the nearest one in the other modality, and therefore retrieve the closest in the other modality. So going from image to retrieve the nearest caption, or vice versa. Okay, so that's coordination. Fission is this other final example where you start maybe with 2 elements, and now you're trying to learn a partition space that has more representations than the number of modalities that you started with. And this can be very useful if you want to learn more disentangled and more interpretable features, where some of them captures overlap between the 2 of them. One captures what's unique in the first, and one captures what's unique in the second. Right? So now you have 3 representations for 2 modalities, and you could go even more. Right? So 3 general ways of learning representations, divided by whether you're reducing and combining representations to keeping them separate, to actually learning more representation that captures different information. All right, so that's the first challenge of representation. The second challenge is alignment. So as we've seen in representation, we just focus on one element in one and one element in the other. Of course, in most problems, you have elements in some sequence following some structure. Right? You have words that you're saying across time. You have image regions in some spatial image. You have sensory data also across time. So alignment essentially studies this problem of how do you align your modalities at both the element level and at the global level. So one example is, for example, if I'm saying something and trying to describe an image, which word that I'm describing, for example, a person, actually matches the image region showing the person. Right? I'm saying hockey stick, which part actually relates to the area of the image that says hockey stick. So learning this mapping between your modalities that captures the parts that have similar semantic information. So several sub-challenges here. One sub-challenge is the easiest case where your modalities are all subdivided into discrete elements. For example, words are discrete, image bounding boxes are discrete. And the goal is to essentially learn this mapping. Which word corresponds to which region in the image? Which other word represents some other region in the image? So solving this matching problem to find the alignment between your two modalities. So that's called learning discrete connections. A second sub-challenge is a more difficult version where you no longer can segment your data cleanly into discrete boundaries, and your data is more continuous. So let's say you have some high-frequency sensor data, medical data, and so on. So it is continuous sensor data. And at the same time, I want to align it with something a doctor is writing. This part indicates that your heart is palpitating. This part indicates that a person fell down. So how do you do this segmentation while also matching it, aligning it to the other modalities? So you have to add this step of doing this segmentation and discretization of continuous data. And while the first two aim to just achieve the alignment, and that was the goal, just to find a matching between the modalities, this third challenge is to use alignment to learn a better representation. Right? So we call that contextualized representations, doing better representation learning by contextualizing how it matches with other parts. A lot of work nowadays in multimodal transformers essentially falls into this, because I'm trying to learn a better representation of some language by looking at other words in its context, and perhaps also looking at parts of the image that are given as context. Right? All that is to learn a better representation of words by taking into account how it's aligned with other words and maybe other images, other videos. So sometimes we also call these two explicit alignment, because alignment is explicit and the alignment is what you're trying to do as an end goal. We sometimes call this implicit alignment, because alignment is just some intermediate step to learn a better representation. Challenge 3 is reasoning. So we've seen in representation, how do you represent one element in one and one element in the other? In alignment, we've looked at how you could learn the connections between multiple elements and multiple elements. Reasoning essentially aims to take all this information and combine it with multiple inferential steps to make some prediction. And when you think about combining information through multiple steps, at some point people were doing it using multiple layers of neural networks that each learn more and more abstracted information that's closer and closer to what you want to predict. But nowadays, as all of you have seen on social media, there's a lot of interest in kind of doing this reasoning more explicitly, right? Am I combining my information in a tree structure, in a graph structure? Do I use attention maps to say, I first look at this part of the image that a person is behind the other one, and then I look at this part of the image to show that the person fell down, and so on. Or nowadays, you can even use words as an intermediate medium for reasoning. You have these LLMs that can not just make predictions, but can really explain step by step. I first do this, then look at the image, then combine it with this, and therefore this is what disease the patient might have. Words can also be used as intermediate step to reason. So a lot of work in reasoning is about first defining what the structure is. Is it sequential, one step to the next? And how many steps? Is it some tree or graph? How do you parameterize intermediate steps? So there's attention maps, which are more visual, words, which might be more language. And of course, you cannot do reasoning without some external knowledge. You need to know about the problem and know what a good reasoning sequence is before you can do it for AI systems. Yeah.
Do we know if reasoning actually improves multimodal inputs? Like chain of thought is typically used in just the language domain, but I've seen a lot of examples where if you use chain of thought reasoning with an image, that it actually performs worse.
We're going to have a whole lecture on reasoning and state-of-the-art reasoning. So only things that happened in the past year. My students are helping me prepare that lecture, and they'll be helping to give it. The answer is reasoning in language is easier. Reasoning with images might be harder. For example, visual chain of thought is harder. But if done right, there is lots of potential. Right? So we have some research going on that, let's say you want to solve a geometry problem. Some starting figure and some question. It'd be very intuitive if the system could do step-by-step the mathematical proofs, while also step-by-step drawing and annotating. I'm looking at this angle, I'm drawing this perpendicular line, this makes it a right angle triangle. All these are visual steps. And if done well, you can improve performance. and more importantly, make it more understandable for humans. You want to actually give it to a student as a tutoring system, you need this intermediate language, visual, and probably more forms of more mediums of reasoning. So we'll look at all this. Sorry, it wasn't clear. This is an overview. And we're gonna look at the specific models for each challenge in the subsequent lectures. Yeah.
So, coming back to that question, there is one paper, Cosmos, which is based on multimodal chain of thought. You have the model on different geometrical patterns, then on image classification, image captioning, and they also then all the human steps that they came with multimodal model on that. And they have shown that it actually improves the so it's in this Cosmos, KOS NOS. Thanks.
Great. All right. Challenge 4 is generation. So you've seen mostly predictive systems that align and fuse and make some prediction. And of course, there's a lot of interest in building generative models that are able to operate across different modalities. So there's one in summarization, so you take more data, you summarize it into the most important features. There's translation, where you take one modality and try to map it exactly to the other. So text to image generation, for example, text to video. And creation is kind of a holy grail, but no one's really been able to do it successfully. When you start with less data, perhaps like a first frame, and you try to generate multiple frames to make an image into a video, or make even like music soundtracks where video and audio and music are all synchronized and generated at the same time. So that's generation. Also work in multimodal generative models. Transference is his fifth challenge, where you might be trying to make prediction in some modality that you care about, say medical images, but you don't have that much data. Okay? In medical, you don't have that much data, you don't have that much labels, and even if you do, it might be noisy. But many reasons why prediction in just the one that you care about might be unsuccessful. And the goal is to use some extra modality to help you support your learning and to learn a better representation for the primary one that you actually care about. Right. So nowadays, for example, you could use LLMs to supplement image classification models. You could use, back then you could pre-train on ImageNet as a second modality to support, medical image classification. Many examples of using one as extra information to help the primary modality you care about. So several ways of doing that. One is to maybe pre-train and then initialize. We'll cover lots of examples of this. There's this set of methods called co-learning, where you introduce some extra information either as an input during training or as a prediction target during training. Right? So if you introduce it as an input during training, you would just zero it out during testing. So during testing, you only have the modality that you care about using inference on. And if you use it as a prediction target during training, you also don't need it during testing. So it's also just operating on the one that you care about during inference. So ways of supplementing more data as input or more training objectives during training to help you get to a better model. And finally, model induction, class of methods where you keep classifiers separate, but again, you encourage them to share some information so that something really good classifier, strong classifiers can help weaker classifiers. Okay, and the final challenge is quantification. So challenges 1 to 5 are more about building, designing new models. Challenge 6 is more about better understanding this entire space, from your data to the models that you build to the training objectives and evaluation. So, I say a lot of words, but measuring how different modalities are formally is still a challenge, and understanding how it influences how the models are optimized and trained is still an open question. Right? Lots of heuristics, no deep understanding. We have intuitions on when modalities are redundant or give unique information, but again, none of these are formalized. Can be made formal through actual estimators. It is not clear how this can again influence the learning process. So quantification contains a lot of challenges on just better understanding things, understanding when they work and when they don't work. All right. So the summary of these 6 challenges, representation and alignment are probably the most important. Given any problem, You're going to break it down into the elements, break down these large data into individual elements, and you have to first decide how to represent your data. Are you looking at fusion problems, so the goal is to combine? Are you looking at retrieval problems, where you might want to keep things separate and align them? Are you looking at maybe fission problems? Alignment is this problem where now you're trying to match different parts of one side to different parts of your modality on the other side. And often you do representation and then you have to think about alignment. And once you've done that, it'd be great if we always did reasoning so that you could maybe break down your problem step by step, explain step by step what's going on in language and vision and more modalities, and use that to predict your label. When you don't care about predicting your label, sometimes you care about generating more data, and sometimes you care about transferring information from one to the other. And of course, although it'd be great if we did reasoning all the time, sometimes people skip over the reasoning step. And most things are just black box over here. And finally, quantification is kind of this magnifying glass that revisits these previous challenges and tries to really understand when things work and when things don't in some principled manner. All right, so this is a quick intro to multimodal challenges. Any questions so far? Great. So in the last about 15 minutes, I'll try to cover some parts of alignment. Next week, we're going to cover everything about fusion, but alignment is kind of shorter, so I'll just cover it in maybe 15 minutes. So as you recall, this alignment challenge is broken down into three. It's all about looking at elements in one and elements in the other and trying to find out where the connections are, where the matchings are. It's the easiest when your data can be broken down into discrete elements, like words and maybe bounding boxes. It's going to be harder when your data is continuous, so you've got to solve this question of taking continuous data and breaking them down into semantic boundaries before doing alignment. We'll cover later in the class this idea of learning implicit alignment. So using alignment to learn better representations, like in these large transformer models. Right? So again, in discrete alignment, one example here is you might try to tie language, which contains words and phrases, to non-linguistic elements that are more visual. So for example, a woman reading newspaper, right? You might have data that's only given at the high level. So entire sentences with entire images, and maybe your goal is to first align the entire sentence with the entire image at a global level, but also maybe at a more fine-grained level. Where does the woman correspond to? Where does the newspaper correspond to, and so on. And a common class of ways of doing this is contrastive learning. In most of these settings, your supervision will come from some paired data. So this is maybe one image with a corresponding caption, another image with another caption, a third image with a third caption. You can get this from Instagram, Wikipedia, Flickr. These are all common data sets with paired data between image and text. Of course, if you want to do it for some other application that's not image and text, you can think about how to get this paired data. And oftentimes, these representations are learned by putting two elements through separate encoders, each getting some representation, and you're trying to enforce some similarity function between the two of them. And this similarity function is what captures the fact that these two representations are aligned. These two representations should not be aligned. They should be further away. Okay? So that's usually some similarity function that you can define. All right? So in contrastive learning, what you would do is you try to make this similarity function really high or really close together for these positive pairs. So images and the actual captions they correspond to. And everything in red are what we call negative pairs. So it might be an image and the incorrect caption, right? There might be multiple incorrect captions for that image, and you will try to make this similarity function smaller, so not as similar. Right? And you can even prove that these kind of methods, they essentially can provably learn the common information between two modalities. So if you formalize common information by the mutual information between these two random variables, then these class of contrastive methods essentially keep everything in the middle and discard everything that is unique in one and not present in the other. All right, so that's a high level, view of what people do in learning these connections. So a bit more formally, these encoders can be designed, they can be very specialized. So we saw like this roadmap of different model architectures, right? You have spatial data, you might use spatial methods like CNNs or vision transformers. If you have sensor data, you might use other encoders. So the encoders can be very different. They'll capture what's unique about each modality. And this alignment similarity function would essentially capture the connections, right? Which representations should be connected to each other and which ones should not. So several choices here. What is FA? What is FB? What are your specialized encoders? And also what is this G function, this similarity function? And once you've designed those, so FA on the first, FB on your second, you then compute this similarity function G between those two representations. And your loss would essentially be maximizing the similarity or maybe minimizing the distance between those representations. And the parameters that you can update are any parameters within FA, FB, your encoding models, and perhaps any parameters in this defining the similarity function. So several choices of such a similarity function. Cosine similarity is a common one. So you learned ZA for the first and ZA for the second. These are our vectors. And cosine similarity essentially says, are these vectors pointing in the same direction in the embedding space? Very simple to compute, essentially a dot product normalized by the norms of those vectors. People have also designed kernel similarity functions. So you can think of, for example, the dot product as basically just measuring whether these two vectors are nearby in the original space, or we call it a linear space. There are also ways of essentially projecting those vectors into some other more expressive space and measuring how similar those embeddings are in that more expressive space. We call that kernel similarity functions. Again, not super important that you understand the details, but just understand that you can measure the embedding in the original space. Measure the similarity in the original space of the embeddings. You can also measure the similarity in some transformed space that is more expressive of the embeddings. Something that has also become quite popular are correlation-based methods. So maybe you don't care about just two embeddings being very close to each other, but given a batch of embeddings, you want them to be correlated with each other, right? So 32 images and maybe 32 captions, you want them to be correlated perhaps across some axes, right? So things that are perhaps outdoors should all be on this side. Things that are more indoors, maybe on this side. So these are correlation-based methods. And you can also investigate, again, if you don't care about just one element in one matching one in the other, you can define these similarities based on pairwise relationships, right? So for example, again, a pair of images, these are very similar, and I want the pair of captions that describe the image to also be very similar. So these are methods that go beyond defining similarity at individual data points to across multiple data points. All right. So visually it looks like this. You might have paired data, images on some side, descriptions on some other side. You would define positive pairs as those that actually correspond to each other. For example, blue car, yellow bus, these actually correspond to each other. Negative pairs are those that are incorrect captions for your images. And you're essentially training this function that maximizes the similarity for the positive pairs. So maximize that value and minimize the similarity for your negative pairs. Yeah. And your similarity function can be something like cosine similarity. And although this is a very simple idea, but it's been around for a long time and it gives you some really, really cool results. So now that you've learned this kind of common embedding space that brings your blue cars next to the text for it and your red cars next to the text of it, you can do this kind of manipulation. You can take in a blue car, embed it into your embedding space, minus the word embedding for blue, plus the word embedding for red. That gives you another embedding. And you will try to retrieve the nearest image corresponding to that. And you actually get red cars. right? You can take this is another cool example. You can take this cats in a bowl, embed it into your space, subtract the embedding for bowl and add the embedding for box. These are word embeddings. That gives you another embedding, and you find the nearest image, and you actually see cats in a box. And this is 2014 stuff, right? This 2014 stuff. Images might be a smaller resolution. Words are just 2 words looking at like bigrams. And of course, nowadays people have already scaled these systems up. Right, nowadays, you have probably seen CLIP, which is essentially an example of scaling up these alignment-based methods. Right, you have millions of images, billions of captions describing these images, and you can again compute this similarity matrix, where entries on a diagonal represent those of the image corresponding with the right caption, right? And those should be similarities that should be maximized. So bringing those together. And everything that is off diagonal would be representing images with wrong captions. Everything is off diagonal. So those similarities should be minimized. And all of these things here are just a cosine similarity dot products, right? Image embedding, dot product with a text embedding. And that's really basically this contrastive loss that you often see nowadays. Sum over your data points, take the average, take the log to make things more numerically stable, but essentially maximizing the similarity of your positive points, and you're minimizing the similarity of your negative points. And sometimes people add the positive points here as well, just for computational simplicity, but essentially just going to be dominated by all the n-1 negative pairs. All right, and again, a similarity function is cosine similarity. Cool, so CLIP is very useful because now you can do something that's zero shot. Zero shot in the sense that after you've trained this, you can give it a new image. This thing that looks like a television studio. And previously, when people wanted to classify what's in an image, they have to train specific image classifiers that could only predict 5 classes or 10 classes, right? If you pre-train on ImageNet, you have to have a fixed, defined number of classes. And one of the biggest benefits of CLIP is now you could do this idea of open set classification. So any caption or any class that you want to classify your image into, you can just give it a list, give it as a list to the model. And what the model would do is that it would embed the image into the feature space. It would embed each of the potential classes or captions into the feature space and take the dot product. So maybe one of this is a higher similarity dot product, some of them lower similarity dot product, and it would essentially give you a normalized score so that you can classify it into any categories that you want. It doesn't have to be a fixed predefined set of 1,000 ImageNet categories. All right, so you can see it does really well on these zero-shot classification tasks. As I mentioned, you can think about the relationship between what alignment does using contrastive learning and what information it captures. So we saw that modalities can have connected and unique information, shared and unique information. You define shared information through the mutual information, and you can prove that contrastive learning essentially captures the mutual information. So it learns this, and it will throw everything else away. Okay, and that is something that you can actually prove. Which is both good and bad, which means that if you're caring about what is common, then these alignment-based contrastive methods are really great. You're guaranteed to keep this and throw away everything else. It's a very scalable method. But if you care about what is here and what is here, then you're in trouble. Because the more you do contrastive learning and the more alignment that you do, the more your performance will get worse. You're throwing away the information that you actually might care about. Several ways of dealing with this. We have some work, other folks have also some work. Very easy to modification, where you can do contrastive learning across your modalities. So you will take image and your caption, and you will do your contrastive learning. That keeps the information in the middle. If you want to keep what is unique in image, then you will take image and you do, in some sense, image only contrastive learning. There are ways of doing that. You take the image, you kind of modify it a little bit, and then you do contrastive learning only in the images. And you should be intuitive that you also do this alignment-based contrastive learning only in text. So you will take the caption, you will modify a little bit, and you will do contrastive learning only in text. And then you can learn what is both shared and unique across your data. All right, I'm just going to quickly go through this continuous alignment. Most of these are references. Continuous alignment is harder because now you have continuous signals, so it's not discrete elements. And usually what these methods do is that they basically recover and try to break your continuous data down into discrete parts. I'll leave some references for people here because I know some people are working with sensor data and videos. There are ways of, for example, taking continuous data and learning discrete boundaries between them. So well-studied problem in computer vision. For time series data, some of my group is looking at change point detection. So they can automatically break into apart your sensor data into discrete boundaries. And each of these boundaries should be semantically meaningful. For example, this is when the person was sleeping, this is when they were awake and exercising, this is when they're working, and so on. So there are ways of automatically breaking down continuous data into discrete boundaries, each of them with some semantic meaning. So you could align it with text, for example. And finally, another class of methods for speech, which is very common, again, continuous data, find some boundary, fixed sampling boundary, get your continuous data, and then do clustering. Right? So clustering is one way of turning something that is continuous into discrete embeddings. So maybe just 3 clusters, and then you can do your self-supervised learning transformers to predict discrete tokens. All right. Okay. So I'll just end it here. We looked at introduction to multimodal AI, several key challenges of data being heterogeneous. There's some connected shared information between them and how they might interact to fuse and get some label that you care about. We looked at several challenges, and we also dived deep into alignment. All right. And just quick reminder, again, reading assignments due tomorrow in preparation for Thursday's discussion. And make sure you make progress on your project so that you could meet with myself and the TA every week. All right. Thanks, everyone. Yes.